Hey everyone, welcome back. I'm really excited for this deep dive.
Me too.
Yeah, always got to stay on top of the quantum computing world, right? So much going on so fast.
For sure.
So get this. We're diving into Majorana zero modes.
Oh, wow.
Yeah, they sound like something straight out of Star Trek.
Right.
But this is real physics, and it could completely change quantum computing as we know it.
You know what's fascinating about this? We're not just talking theory here. Microsoft has actually built a chip,
Oh, wow.
the Majorana 1, that uses these particles.
That's incredible.
Yeah.
So that's what makes this paper so fascinating. Majorana zero modes in topological superconductors. Implications for quantum computing and unified field theory.
What a title.
I know, right? It's a mouthful, but I knew you'd be all over this
Oh,
one.
yeah, this is right up my alley.
It explores how these tiny particles could not only revolutionize computing, but also offer clues to the biggest mysteries of the universe. Pretty wild.
It really is. The paper takes us on this incredible journey from the microscopic world up to the vastness of the cosmos.
Okay, so let's start with the basics for our listeners who might not be familiar.
Sure.
What exactly are Majorana zero modes, or MZMs for short?
You know how, like, at a concert, you see a wave going through the crowd?
Yeah.
You've got all these individual people, but the wave acts like its own separate thing, right? That's kind of what a quasi-particle is like.
I see.
MZMs are these quasi-particles that emerge from the collective behavior of electrons in certain materials.
So it's like the electrons are doing like a synchronized dance, and this MZM is the pattern that emerges.
Exactly.
Okay, I kind of get that.
But here's where it gets really mind-bending.
Okay.
The paper describes these MZMs as being their own antiparticles.
Now you've lost me. I know a bit about antimatter, but that just sounds bizarre.
It is a bizarre concept, but it's key to why MZMs are so special.
Okay.
So you know how every particle has an antiparticle, kind of like its mirror image?
Right, like an electron has its positron, a proton has an antiproton.
Exactly. It's like the universe has this bizarro world version of everything.
Uh-huh.
But MZMs are unique because they are both particle and antiparticle at the same time. It's like looking in a mirror and seeing yourself and your opposite simultaneously.
So if an MZM is its own antiparticle, does that mean it can't annihilate itself? Does that make them more stable?
That's exactly right.
Yeah.
Because they can't annihilate themselves, they are incredibly stable. And you know how fragile quantum states can be?
Oh yeah, for sure.
This stability is what makes MZMs so exciting for building more robust quantum computers.
That makes a lot of sense.
Yeah.
You mentioned Microsoft's Majorana 1 chip earlier.
Right.
How does it actually utilize MZMs?
They've created this really clever hybrid system
Okay.
using indium arsenide, a semiconductor, and aluminum, a superconductor.
Mm-hmm.
It's within this specialized environment that these MZMs can emerge.
Interesting. So it's like they've engineered the specific material recipe to cook up some MZMs.
Yeah, you could say that.
Right.
But it's not just about the materials.
Right.
You also need to fine-tune certain conditions, like the spin-orbit coupling, the Zeeman splitting, and the superconducting pairing.
Okay, hold on. Those are some pretty technical terms. Can you break those down for me and for our listener in a way that doesn't make our brains melt?
Of course. Imagine an electron spinning like a top as it moves through the material.
Okay.
Spin-orbit coupling is like a link between that spinning and its movement, and it's crucial for creating the conditions for MZMs to emerge.
I think I'm following you.
Okay, good. And think of Zeeman splitting like using a magnet to separate electrons based on their spin.
Gotcha.
And superconducting pairing allows electrons to buddy up and behave in a way that enables superconductivity.
Okay, I think I'm starting to get the picture. So by manipulating these different factors, researchers are essentially creating the perfect environment for MZMs to pop into existence.
Exactly. It's like setting the stage for a very specific quantum play.
I like that analogy.
And this is where the math comes in.
Uh-oh.
The paper utilizes something called the Bogoliubov-Digenus Hamiltonian.
Now, I'm not going to ask you to break down that equation, but for those of us who aren't theoretical physicists, what's the key takeaway from that model?
Think of the BDG Hamiltonian like a powerful simulator.
Okay.
Physicists use it to model how electrons behave in this complex material system.
So it's like their crystal ball.
Kind of, yeah. And you know what's really cool? It was this model that actually predicted the existence of MZMs.
Wow. So it's not just a theoretical concept. There's an actual mathematical framework that supports their existence.
Precisely. And here's something really intriguing.
Okay, what's that?
The BDG Hamiltonian doesn't just describe MZMs. It also predicts that the system undergoes a topological phase transition when these MZMs emerge.
Okay, you've got my attention. What's a topological phase transition?
Think about water changing from a liquid to ice.
Okay.
It's a dramatic change in the properties of the system, right?
Right.
That's a phase transition.
Makes sense.
A topological phase transition is similar, but it's the system's overall structure that changes abruptly, kind of like flipping a switch,
Right.
which leads to the emergence of MZMs.
So it's not just a smooth, gradual change, it's a sudden shift in the system's behavior.
Exact.
Fascinating.
It is. And the shift is marked by a change in the system's topological invariant. Think of it like a mathematical fingerprint that captures the system's overall structure.
All right. I'm following you so far.
Good.
We've got these MZMs. They're stable. They're potentially game-changing.
Right.
But how do they actually work in a quantum computer? That's where things get really interesting. So we've got these stable MZMs. They sound like a quantum computing dream come true.
They really do. But how do they actually do calculations? That's where things get even weirder.
Even weirder.
And even more exciting. We have to talk about non-abelian ennions.
Oh boy, another one of those terms.
I know it's a mouthful.
I had to look that one up too. What are these non-abelian ennions and what do they have to do with MZMs?
Remember how we talked about those quasi-particles being like emergent phenomena, those patterns from lots of electrons?
Yeah.
These non-abelian ennions are closely related to MZMs.
Okay.
And the really cool thing is that they can interact with each other
Okay.
in a way that actually performs computations.
Interact how? Like they bump into each other and spark a calculation.
It's more like a very specific kind of dance.
A chance. Okay.
Think about braiding hair.
Okay.
The order in which you cross the strands matters, right?
Oh, different braiding patterns create different looks.
Exactly.
Yeah.
And are you starting to see where I'm going with this?
Are you saying that these MZMs or these ennions can be braided together?
That's the key. The braiding of these non-abelian ennions is what actually performs the quantum computation.
Wait, so just by moving these MZMs around each other, we can do calculations?
That's the idea.
That sounds like something out of a sci-fi movie.
It might sound like science fiction, but it's based on some pretty solid physics.
So cool.
It's a fundamentally different way of thinking about computation.
How so?
Instead of relying on bits, which can be either 0 or 1,
Right, the classic binary.
we're using the topological properties of these ennions to encode and manipulate quantum information.
So instead of zeros and ones, we're using braids.
You got it. Think of it this way. The information isn't stored in the individual MZMs themselves,
Okay.
but rather in the way they're braided together.
I see.
It's like the information is encoded in the pattern of the braid, not the individual strand.
And that's what makes this topological quantum computing so special.
Exactly. Because even if there are minor disturbances,
Right.
the information is safe because it's in the overall pattern, not the individual ennions.
It's like a safety net for the information.
Exactly. This is what makes topological quantum computing so robust.
Makes sense.
And remember that Microsoft chip we talked about, the Majorana one?
Yeah.
That's a big step towards making this kind of braiding a reality.
This is incredible. It sounds like we're on the verge of a whole new era of computing.
It really does.
But the paper also mentions that there's still some debate in the scientific community about whether these MZMs truly have these non-abelian statistics right.
Yeah, that's a good point. While the theory is very compelling and experimental results are promising, we need more evidence to definitively prove the non-abelian nature of these ennions.
So it's still an open question.
It's an area of active research.
So it's a bit of a wait-and-see situation for topological quantum computing.
Science is often like that. But even if the non-abelian statistics aren't fully confirmed,
Yeah.
MZMs are still incredibly promising for quantum computing.
Okay.
Their stability alone makes them a very attractive candidate for building future quantum computers.
Okay, so even if the braiding part isn't a sure thing, yet MZMs are still worth exploring further.
Absolutely.
It makes you wonder what other secrets these tiny particles might be hiding.
Yeah, for sure. Who knows what we'll discover next?
Well, we've covered a lot of ground here, from the bizarre nature of MZMs to their potential in quantum computing,
We have.
and even a hint at their possible connection to a unified field theory.
It's amazing.
The paper also goes into more detail about the mathematics behind all of this.
Yeah, a lot of equations.
Maybe in the next part, we can take a closer look at some of those equations and what they reveal about these mind-boggling particles.
Sound good to me.
It's amazing to think we started with these tiny particles.
I already.
And now we're talking about the entire universe.
It's all connected.
Yeah. So we've been on quite a journey exploring these Majorana zero modes.
They really are fascinating.
They really are pushing the boundaries of what we thought was possible in quantum computing.
And physics in general.
Absolutely. But as promised, let's dive into some of the math that underpins these incredible discoveries.
All right, let's do it.
Don't worry, we won't go full-on theoretical physicist here.
Uh-huh. No worries. I promise to keep it accessible.
I know you will. So the paper really delves into the mathematical depths of MZMs.
Oh yeah, there are a lot of equations in there.
But I know you can pull out the key insights without losing us in the technical jargon.
Well, we've talked about the Bogoliubov-Degenus Hamiltonian,
Right, the BDG.
the BDG for short, and how it predicts the existence of MZMs. It's a pretty complex
Yeah.
equation, but think of it like a recipe that lays out all the ingredients and steps needed to create these bizarre quasi-particles.
Okay, I'm following you. So what are some of the key elements in this MZM recipe?
We've touched on some of them already. Spin-orbit coupling, Zeeman splitting, superconducting pairing.
Right.
The equation also includes elements that describe things like the electron's momentum, its effective mass, and the chemical potential of the material.
So it's all about fine-tuning those different parameters.
It is.
So by adjusting those parameters, researchers can essentially fine-tune the material system to create conditions where MZMs can exist.
Exactly. It's like they're tweaking the settings on a machine to get a specific outcome.
Okay, I like that.
And remember the topological phase transition we discussed?
Yeah, that sudden shift in the system that leads to MZMs.
That's the one. Well, the BDG Hamiltonian also predicts that.
So the math doesn't just describe MZMs, it also predicts how to make them.
And when this big shift will happen in the material.
Exactly. That's really cool.
It's incredibly powerful.
And this is where it gets even more interesting, right?
Okay, when we connect this back to unified field theory.
Okay, yeah, the big one. The theory that tries to unify all the fundamental forces of the universe.
Exactly, that's right. The paper hinted at a connection between the math behind MZMs and those grand unified field equations,
The UFEs.
or UFEs.
How does that work?
The UFEs, which build on Einstein's general relativity, include a concept called torsion.
Torsion.
Torsion. It describes how space-time can be twisted or contorted.
Okay.
And what's remarkable is that the mathematical structures underlying these UFEs and MZMs share some striking similarities.
Wait, are you saying that the same mathematical language can be used to describe both the behavior of these tiny quasi-particles and the large-scale structure of the universe?
It's one of the most surprising insights of this research.
That's pretty mind-blowing.
It is. It suggests a profound connection between these seemingly disparate realms.
Wow.
And it's something that physicists are just starting to explore.
So we've gone from electrons dancing in a material to the vastness of the universe, all linked by these MZMs and some really cool math.
I love how physics does that, bringing together these seemingly completely different ideas.
Absolutely. It really highlights how the pursuit of knowledge can lead to unexpected and awe-inspiring discoveries.
Couldn't have said it better myself.
Well, this has been an incredible deep dive.
It really has.
Thank you so much for breaking down these complex concepts.
Of course, it was my pleasure.
And to our listener, if you're fascinated by the world of quantum physics and the power of math to unlock the secrets of the universe, I encourage you to explore further.
Yeah, there's so much out there to learn.
You never know what mind-bending discoveries await.
Absolutely. The journey of scientific exploration is never truly over.
Well said. Thanks for joining us, everyone.
Until next time.